Okay, welcome to Reigate College Maths Year 2 Stats. This is hypothesis testing with the normal distribution. So before we talk about hypothesis testing with the normal distribution, we need to talk about a little of the theory behind this. So hypothesis testing we've already met in the context of the binomial distribution and of testing for the correlation coefficient, testing for correlation, and we're now going to see it with the normal distribution. But what we've got to talk about first is the distribution of sample means. So if we imagine that we've got a population which has a normal distribution, so here it is, my variable x is normally distributed with mean mu and standard deviation sigma, so it looks like this. So for example, we could be talking about the heights of adults in the UK. Now what we're going to think about is what happens if we take a sample of those adults. So take a sample of 10 adults, and then we're going to calculate the mean of their height. So we're going to say their mean height is x bar, and we're going to call this x bar 1 for the first sample that we take. Now that mean there is a new data item, and it's going to fit somewhere on this scale if we were to draw a new scale, so maybe it fits here. And then we're going to take a second sample. Second sample is equal to, we're going to call that x2, x bar 2, and that maybe is up here somewhere, and a third and a fourth, and so on. And then we're going to put all of these on our scale here. Well, it turns out that these data items, the x bar 1, x bar 2, and so on, are themselves normally distributed, and not only that, but they have the same mean as the overall population does. So we get a distribution that looks something like this. It's actually taller and narrower, like that. Possibly I haven't drawn that enormously well, but that is called the distribution of sample means, and we write it with an x bar, and we can now say that that is normally distributed. It's also got mean mu, and it has variance sigma squared over n. So it depends, that the actual shape of this depends on how big our sample is. So we're going to say n equals 10 for my example with the heights of adults here. So for x bar, that means that the standard deviation of x bar, standard deviation of x bar is sigma, which is the standard deviation over the whole population, divided by the square root of n. Remember that we put the variance in here, and the standard deviation is the square root of the variance. Okay, so that's a crucial thing to remember, that when we are doing, as we will in a minute, hypothesis testing, we're going to be thinking about this distribution of sample means. So what we're going to do now is we're going to think to ourselves, well, if we know, or if we have a hypothesis about the whole population, and we take a sample, maybe it's sample size 10 or whatever size it is, and it comes out to a particular value. Does that tell us something about this population? Does that say to us, yes, it looks like this, we've got this mu correct, or does it not? That's a situation where we're going to think about hypothesis testing. So our sample that we take, x bar, does it give significant evidence that the mean of the population is actually less than we thought it was, or is actually greater than? So let's have a look at how this hypothesis testing works. You'll get the idea of this through working through some examples. So I'm going to take this away here. Let's have a look at the questions that we have in our course workbook. So let's just actually have a look up the top here. So we are going to look at 3 types of tests. So the first test says that the mean of the population is equal to a certain value. The second test is going to say, and our alternative hypothesis is going to be the mean is less than that value. Alpha is just a value of a mean. It's going to be a numerical value when we look at the examples. The second type of test is going to be mu equals alpha, and alternative hypothesis, so it's a null hypothesis. Alternative hypothesis mu is greater than alpha. So these are both one-tailed tests, and then we're also going to look at a two-tailed test which says our null hypothesis is mu is equal to alpha, and our alternative hypothesis is mu is not equal to alpha. So some similarity there to hypothesis testing with binomial distributions. So let's look at question 1 here. So question 1, we have got these hypotheses written out for us. So for 1a, we've got null hypothesis mu is equal to 25. Alternative hypothesis mu is less than 25. We've got a sample size of 10. I find it helpful to write out the distribution here. So we're saying that x is normally distributed, it's got a mean of 25, and it's got a standard deviation, that's what we're given here, of 10. So this is, of root 10. So its variance is 10. And then we can say, well, we can work out the standard deviation for x bar, which is the distribution of sample means. So we can say SD for x bar is sigma over root n, which is root 10 over our sample size is root 10, so it's 1. So x bar is normally distributed, and we've got a mean of 25 and a standard deviation, and therefore also a variance of 1. So what we're going to do is we're going to say we've taken our sample of size 10 and we've got a mean of 23.5. We're going to find if the probability that we get a mean of 23.5 or less is greater or smaller than 5%, so 0.05. So we're going to say we're going to find the probability that x bar is less than 23.5 and compare to 0.05. Okay, so the probability that x bar is less than 23.5, well, let's go and put that into our calculator. So we're going to go menu, oops, where is it? There we are. Menu, then 7 for distribution, and then we want to go down to, we want to go to 2, normal cumulative distribution. Lower, we've got to put in a small value here, so I normally put in minus 1000, and then our upper value is 23.5. Our mean is 25, and our standard deviation was 1, wasn't it? Oops, got those wrong way around. 1 and 25. There we are, and then we're going to press equals, and we get 0.0668 or 0.067. So is equal to 0.067. 0.067 is greater than 0.05. Now what we're saying here is that if the value that we got here, the probability, was less than 5%, then we're saying that this value for the mean is so unlikely that we're going to say that our alternative hypothesis, that the mean is actually lower than what this distribution says it is, we've got some evidence for that. In this case, it's bigger than 0.05, so we're going to we're going to say that the test is not significant. So test is not significant. That's significant at the 5% level. And we're going to reject H1. So we're going to say there is not sufficient evidence that the population mean mu is less than 25. Okay. So remember that the mu is less than 25 was our alternative hypothesis. Okay, so that's the first example. Let's go on to B, and let's go a little bit quicker now. So let's put these on top there. So for B, what we've got is we've got mu is equal to 25, and now we've got an alternative hypothesis of mu is greater than 25. We've got a sample size of 10 again, and we've got x bar is 27 this time. So we're going to say x is normal with mean 25 and variance 10, so standard deviation root 10. X bar is normal with mean 25 and variance sigma squared over n. This is sigma squared divided by n is 10, so we've got 1 again here. We're going to find the probability that x bar is greater than, this is always going to match what we've got here, greater than 27, which is the sample mean that we've got from our sample of data, is equal to, let's go and have a look now on the calculator. So we want to say that we've got now lower of 27, upper of something large, so 1,000 will do, and then we've got the same mean and standard deviation there, and we get 0.023, 0.023, and 0.023 is less than 0.05, which is the 5% significance. So we're going to say, so the test is significant. We can accept H1, and we can say there is evidence. We sometimes say at the 5% significance level that mu is greater than 25. All of these tests, of course, do depend on what significance level is chosen. Okay, let's go and look at C now. So for C, this time we've got a two-tailed test. Mu is not equal to 25. And we've got a 1% significance level, so much smaller significance level. So let's write out our distribution again. X is normal with mean 25, and standard deviation again is root 10, so variance is 10. This time n is equal to 250. So the standard deviation of x bar is, well, we want sigma over root n, so that's root 10 over root 250. And that's equal to, well, we can take out a root 10 from there, so that's 1 over root 25 is 1 over 5, or 0.2. So x bar is normal with mean 25 and standard deviation 0.2, so variance 0.2 squared. Or we could write that as 1 over 5 squared or 1 over 25. It's a two-tailed test, and as we've seen before with binomial hypothesis tests, that means we split to the significance level to half of it for each tail. So two-tailed, so 0.005 each tail. Now, if we look at the x bar, it's 24.5, so that's our sample that we've taken from the data. It's actually lower than 25, so the tail that we actually need to test in practice is only one end. We can see that the probability that this is going to be greater than something is going to be very large. So it's the probability that x bar is less than 24.5 that we're interested in. So probability that x bar is less than 24.5 is equal to, well, again, let's go and look it up on the calculator. So let's cancel that, and what we need is a lower value of something small, minus 1000, upper value of, what did I say, 24.5, a standard deviation of 0.2, and a mean still of 25. So we press return there, we get 6.2 times 10 to the minus 3, so that's 0.0062. 0.0062. Now we're going to compare that to our significance level. Well, it's bigger than our significance level, and we need it to be smaller than our significance level. So test is not significant. Reject H1. Okay, and we stick with our null hypothesis. So there is insufficient evidence that the population mean is different from 25.